Right, welcome to pretty much the last episode of Simple Harmonic Motion. We're going to focus in this one on a pendulum. Now, a pendulum is a little bit more complicated as we have to make one geometric assumption in order to get a nice equation to work on. But let's first draw our situation. So we have a pendulum attached at a point, and let's just draw some construction lines, get an idea of what's actually going on here. So this is straight down. Apologies, that is not. We have an angle. We like angles called theta, and we have the oscillation that goes like this. This distance from here to here, we're going to assume is straight, and we're going to call it S. And then distance here, we're going to call it L. Let's do a free body diagram of this. Somebody's sending me emails, which I don't want, although some people might say I need it. Let's look at the free body diagram. So same situation. We have, I'm just trying to avoid to press one of the buttons on my little stylus here. We have the bob here, same bob as this one. Gravity is working down, and that's of course mg, and in this direction here and this direction here, we have two forces that construct together, or that we can actually use as forces in their own right. Now this one here, if this angle here is theta, which is the same as, oops, terrible, this angle here theta, then this component is mg sine of theta, and the one that's perpendicular to the motion, that's this one going in this direction here, that's mg cos of theta. Now keep in mind that the restoring force in this case is actually the restoring force F is going to be equal to minus mg sine theta. Now using, I'm going to go to vector format here, Newton's second law, we have that acceleration is equal to the restoring force is minus mg sine of theta divided by the mass. The mass cancels out, so we get the acceleration is minus g sine of theta. Let's remind ourselves that the acceleration is equal to minus omega squared x, and in this case x is s. For angles of theta less than approximately 10 degrees, sine theta is very, very close to S over L, which is this over that. Now this is a very important thing. I haven't seen questions on this, but I think with the more complex exams that we're now having since 2015, this approximation and an understanding that this approximation of making the division of S over L equal to theta can, I would guess, come up as a question during an exam paper, and maybe they would push you to maybe pushing the pendulum to say 20 degrees and ask you why your calculations no longer work. It is only for very small or smallish angles of say 10 degrees and smaller that this approximation actually works. We can now re-express this our situation here by saying that A is equal to, go back up here for a moment, minus G S over L. And if we just remember that these two are essentially the same, we end up seeing that using the equation here, that A is actually equal to minus G over L times S, where S is just our kind of pendulum version of displacement along the line of the arc that it actually is encompassing. And if we now just take into account this and this, we can actually re-express this and say that omega squared is equal to G over L. Well, this has interesting implications. Keep in mind from circular motion that omega equals 2 pi f, and if we express that in terms of its period, 2 pi over t, we can create a formula where we have an equation where we can work out either the period or the frequency if we know either of these two here. Again, I'll do this in two different locations and slightly different colors. So let's take the period version of this and say that take this one here and here. So omega squared is equal to, we square this expression here, 4 pi squared over t squared, which we now know from here is G over L. But remember, this is only for angles of theta less than 10 degrees. So when you perform this practical, make sure that you're not going any further than that 10 degree angle. Solving this for t, and again satisfy yourself that this rearrangement is correct. We're in year 2 now, so you should be able to do this fairly simply. We get t squared is equal to 4 pi squared L over G. Taking the root out of both sides, we get 2 pi root out of L over G. Similarly, for the frequency version of this equation, we just simply invert both sides. So F, the frequency, is 1 over 2 pi root out of G over L. So if we, this is t, not t squared. So if we graph t squared against the length, so that's the length here, we will get a graph against the length where the gradient is 4 pi squared over g. So once we know the gradient, we've just solved the gradient for 4 pi squared over g, and we can calculate gravitational pull of whatever planet we happen to be on, presumably Earth.